Sir, good afternoon, sir. We welcome you, sir. We welcome you from the ATAL FDP team, sir. కొద్దిగా మళ్ళా అదే ఎందుకు
తెలియదే ట్రబుల్ షూటింగ్
Google Meet
Google Meet keeps closing. It might be a minor system glitch.
by
You can fix.
restarting your phone.
సార్ది రీస్టార్ట్ చేయాలి. సార్ ల్యాప్టాప్ ఒకసారి రీస్టార్ట్ చేయమను. మొబైల్ అయితే మొబైల్ రీస్టార్ట్ చేయమను. Custom skins and Android version, but you can reboot most Android devices by law. Count for 10 seconds అంతే. రీస్టార్ట్ చేసేస్తే వచ్చేస్తుంది. సార్ అది ఒక్కసారి మీ ల్యాప్టాప్ కానీ మొబైల్ కానీ రీస్టార్ట్ చేయండి సార్ అని రీస్టార్ట్ చేస్తే వచ్చి అలా ఉండదు సార్ అని చెప్పి. Good afternoon, sir. Ram Kalyan, sir.
Yeah, good afternoon. Am I audible now?
Yes, sir. It's audible, sir. It's clear, sir.
Okay, I'm sorry for the delay. There was some, every time it started switching off for me. So let us hope. Let us hope now it works.
Yes, sir.
Yeah, I'll try to share first, and then we can.
Sir, we welcome you from this Sri Vidyaniketan team for the ATAL sponsored FDP on mathematical modeling and controller design for nonlinear process, sir.
Yeah, thank you.
We will have.
Yes, sir. It's visible, sir.
Okay. Yeah.
Sir, 1 second, sir. Let me introduce myself.
Sure.
Good afternoon, participants. It's my honor to read out the profile of our today's resource person, Dr. Ram Kalyan Ayyagari. He's a professor, Department of Instrumentation and Control Engineering, NIT Trichy. He completed his BE in Electronics and Communication Engineering and ME in Control Systems from Andhra University, Visakhapatnam in 1990 and 1993 respectively, and PhD in Control Systems from IIT Delhi in 2000 on the topic Robust Output Feedback Controllers for Nonlinear Systems. His research areas include mathematical control theory, including circuits, signals and systems, numerical linear algebra, complexity theory and randomization, neural networks and learning algorithms, cyber physical systems, modeling and intelligent control of big data systems. He delivered innovative lectures and talks on various topics in IIC Bangalore, NIT Calicut, PSC Coimbatore, DRDL Hyderabad, NAL Bangalore, IIT Bombay, and in University of Leicester, United Kingdom. He authored 2 books with title Control Engineering, a Comprehensive Foundation, and Linear Systems Analysis and Synthesis. He received Young Scientist Award by Government of India, Ministry of Science and Technology, and Summer Research Fellowship of the Indian Academy of Sciences, and Major Award towards Reliable and Smart Air Vehicles. He has many projects and he published in various peer-reviewed journals and conferences. Most of them are IEEE transactions. We welcome you, sir, for this 5-day FDP on mathematical modeling and controller design for nonlinear systems. We are eagerly waiting for your session, sir. We welcome you, sir.
Good afternoon, everyone. Thank you so much for your kind invitation to be a part of your FDP. Your institution is quite familiar to us at NIT Trichy because quite frequently we get our MTech students from your college. So we have a good appreciation and respect for your institution because you are able to send out some good students who have qualified in GATE with higher scores, and they're also interested in academics to pursue higher degrees with us and so on. So that gives me a lot of pleasure in joining you today for this FDP and try to share whatever little I might have known and learned for several years. Uh, without taking much time, um, I just wanted to introduce some of these basic ideas. Control systems is a very, very important subject. Maybe up to 10 years ago, it was lying dormant. Actually, there were lots of articles, many places where it is boldly written that without control there is no technology. But still, until 2015 or so, people were reluctant to appreciate the importance of control systems. We have experienced it very bitterly, rather, in the early part of our careers during our PhD and all these things. But down the line, from 14, 15, say about last a decade or so, broadly, there is a lot of emphasis on this because, uh, as somebody pointed out much earlier, without control, there is no technology. So control has to be implemented properly. And control is no longer, first order, second order models and PID control alone. The systems you are trying to understand, the systems you are trying to control, the physical systems I'm talking about, not the models. The physical systems are quite complicated. In fact, we are making them more and more complicated day by day. Just look at your cell phones, how often we have to change the cell phones. I'm trying to say that this is much more often than changing your desktops or laptops, apart from the cost. Some change, a radical change, will simply put your previous version of the phone just away. You may have to buy a new one. So such rapidity in developments demands, or rather is a consequence of adding more and more details. And these details are very well received in the market. So naturally, modeling must accommodate these details as well. So in a sense, what I'm trying to say is that if you say, or rather if you continue to say that I'm happy with first order, second order models, it's no longer going to work. You need to go with higher order models. Here, order means details, more details, more details. It's actually a kind of paradox to me. Of course, others um, who are already working in these areas or other experts who have kindly agreed to deliver lectures in this FTP may pardon me if I'm wrong. We are talking on one side about fractional PIDs and things like that, but at the same time, it is still a PID. It's a paradox to me. Fractional geometries and other things are more towards, wavelets and such things. If you are basically at least familiar with that, so it is something like looking at a square, not just like a square, or a circle just like a square circle, but something like, you'd have seen the Monaco biscuits with edges in a slightly clogged manner. Right? They are not perfect straight lines anymore. You have slight curvatures. That's why we talk about dimensions like 2.14, 2.7, things like that, not integral dimensions. So that's a totally different science altogether. But the point is, we need to accommodate details into our models step by step, and we need to enlarge. We need to see what are all the pitfalls that might come in this. What are the challenges that we may face? In what way we would like to overcome these challenges, and then uh, design much better systems. At the same time, we should also allow more development to happen within this same framework. That's also important. We have to foresee what may happen in the near future, and can that also be accommodated in our framework. That's a real challenge, and that's actually a real contribution, which down the line will put you on a more successful platform. So in that spirit, I would like to hit a note on this. So I'm talking about details, accommodating details. So these details for us are typically twofold. One is that we need to look at more interactions. When you have a system, uh, when you have some kind of a connection, for example, if you recollect your basic first course on control systems, and you are introduced to block diagrams. So what is the fundamental assumption we have? The signals from one block to the next block, possibly in our convention we write it to the right side of the first block, right? The signals are delivered to the following block in only one direction. The other block will not respond back. That's our fundamental assumption. But in general, it need not be so. So, for example, just take your simple RC network, right? It doesn't mean that current flows only from the resistor to capacitor, but not the other way around. It's not the case. Even if you work out and, for example, look at the expression you get for a simple voltage divider, R2 by R1 plus R2. So you can actually rewrite it as 1 by 1 plus R1 by R2. So doesn't it look like, G by 1 plus GH? Okay. So in a very simple way, you are able to identify some kind of a closed loop or a feedback of these systems. And a very closely related illustration I can give you is when you are designing amplifiers, you always appreciate, for example, an amplifier that has a resistance in the emitter lead. Common emitter amplifiers are much better than other configurations. Therefore, we choose CE amplifiers. And in CE amplifiers, we would like to have a resistor in the emitter lead. So we say actually it serves as a self-biasing circuit because it adds to both input and output loops. So it stabilizes and so on and so forth. So feedback is essential, and feedback is not as simple as trivial as output feedback alone. That's another problem with classical control. A very blunt argument saying that output is the only measurable quantity. Therefore, I'd like to make use of only the output as feedback. Not necessarily anymore. So interactions I'm talking about is this kind of multiple feedbacks in addition to the output feedback. Number two is nonlinearities. Again, if you open any textbook or chapter on nonlinear systems, usually the first sentence is in nature everything is nonlinear. But then what happens? Like the well celebrated essay on cow or aeroplane, you somehow do this and that, argue this way, that way, and then bring it back to linear systems and talk about linear systems. That should not be the case. Of course, about 80, 90 years ago, when people were in the middle of world wars, and there is not much of a concept called research grants and things like that. There were no computers, right? All maybe people like Bode or Nyquist, these people, at the best, they had a bunch of white papers and maybe a pencil or a pen. So they were doing research using those very minimal tools, but they had a wonderful machine called their brain. So they tried to, bring out so many ideas. Just look at the beauty of root locus, right? Just on a plain paper on a graph sheet, you are able to locate what happens to the roots of a polynomial if one of the parameters is kept changing. Right? So such beautiful, brilliant ideas they have created. And I really lament saying that today with powerful MATLAB, we are really not able to create equally brilliant ideas. Right? We are somehow dumb today. Anyway, the other part of it is that those brilliant ideas, because they had limitations in the tools, they had certain limitations. So, for example, because it is a plain paper, it's a two-dimensional, no, this thing. So, beyond second order, they are unable to conceive. Right? How does a fourth order or fifth order response looks like? What are various dimensions? It was, maybe they had ideas, but they were unable to communicate. Therefore, we didn't learn them in the courses earlier. But if you bring that argument along with the development in technology, for example, the computers, and the rapid growth in computing power, right? If you look at it that way, we should not be lagging behind anymore. With good simulations, we should be able to visualize higher order or higher dimensional systems, and we should be able to understand what is going on in more details. And these details need to be fed back so that you have all the interactions appropriately accounted for. And with these interactions and not neglecting the nonlinearities, we should be able to devise better controlled systems. So this is broadly the framework I just wanted to enunciate so that within that we'll be able to discuss some details about a particular concept called feedback linearization for nonlinear systems. It also so happens that there are more popular nonlinear controllers, which I'm sure every one of you would have heard. For example, the sliding mode controller or the variable structure systems. To some extent, maybe you would have seen some papers mentioning about what is called backstepping. These and various other so-called nonlinear controllers are all derivatives of this feedback linearization. So that's why I prefer to call this as the mother of all nonlinear controllers. There are discrete time versions of this. There are computational algorithms available today. It's not a big deal to implement this kind of controllers. We don't have to go back and say that, I have a nonlinear plant, all right, but I would like to linearize it around some operating point and then implement a PID controller. Not necessarily anymore. That's what I'm trying to say. If you talk something about technological limitations, today we do not have such limitations, which we had maybe about even 5-6 years ago. Okay? Today we have fast processors, we have much better sensors to sense, therefore output is no longer the only quantity that is measured. There are many more that can be measured. And even if you would like to design a state estimator, the so-called Kalman filter, or its variants for nonlinear systems, for example, the unscented Kalman filter, these can be very quickly implemented as algorithms. They can be run on very fast systems. Therefore, your data estimation is also done very fast. So we should be able to cope up and bring together some fundamental mathematical ideas together with the technological, rather more specifically computational advantages we have today, and then bring up better frameworks. And as I was a few minutes ago mentioning, our framework should be able to accommodate some of the near future developments as well. Okay. Okay, with this background, I go ahead with my presentation. Maybe it will take about an hour or so. Then we can discuss if there are any doubts, questions, because I'm asked to stay up to 2:45 or so. That's up to you. Or equivalently, please don't hesitate to stop me at any point if you have any specific doubt where you find it difficult to follow or something like that. Then we can spend some time then and there itself and then go ahead. Please feel free. Don't hesitate that you're obstructing my flow or things like that. So the talk talks something about introduction, a little more technical introduction than what I spoke for the last 10 minutes or so. Then some intuitive ideas, obviously, unless we have experienced, we have seen something either consciously or sometimes subconsciously, we will not be able to proceed towards understanding anything. We do have mind blocks. So to erase such blocks, I'd like to put forth certain intuitive ideas. I just make you realize that these are not really new to you, but maybe they're hidden in your subconscious. And then I'll talk something about the linear part of state feedback and how it can be extended. Right? Just now I was also mentioning, if you do something, create a framework, see to it that some future is also accommodated there. If you really see the state feedback that was taught to you, or that's what you have been teaching, or you have been researching in, the state feedback or the state space framework is not just an extension of transfer functions and things like that, which is usually dumped in books like Ogata and other books, right? They are pretty old, but state space methods, in fact, quite independent of the classical control, we will be able to teach as an independent course. Right? So within that framework, how do we bring in nonlinearities? Then for this, what else we require than Laplace transformation is so-called differential geometry. I'll just give a tip of the iceberg because that itself is a big course. But I try to encourage you or motivate you towards taking up such courses as well, and how to employ such ideas into control system design. And then I'll wrap up my talk with some examples, and then we'll conclude with a summary. Uh, this is my inspiration for quite some time. You will see the contrast. One is talking about popularity, the other is about context, relations, and connections to reality. Right? So it's always good. Of course, there are pressures outside to get a promotion, to get a PhD. We may have to do some things that are aligned to popularity, but down the line, what keeps you steady in progress, what adds value to you is the context, relations, and connection to reality. This is my inspiration. I just wanted to share with you as well. Okay. As I notice, I think this FTP is being conducted by the EEE department. So naturally, there will be more electrical people in the audience. Otherwise, also it's fine. It will not be a problem. But I thought this could be a good example, which is familiar to many people. And if I write it in a slide like this in about 5 or 6 equations, not much is really Greek and Latin, but most of it is understandable. But only thing is, not from a purely electrical or a motor point of view, but from a control point of view, I attempted to write the equations governing the induction motor in terms of fluxes, currents, and so on as a state space model. I don't want to read out every line, or I don't want you to read now. But the point is that you see so many state variables, and not necessarily this is a linear system. That's important. Only some assumptions will tend to linearize, but then you can also see as a critical comparison, linearization, how much limitations it will bring in, right? So this is a control engineer's perspective, and we sum up with an equation like this: x dot equal to f of x plus g of x times u. In the linear case, f of x is a matrix multiplied by the state vector, so you get ax. G of x is usually a matrix, a constant matrix b, so you get x dot equal to ax plus bu. In linear case, we slightly extend it, generalize. F of x still could be a product of matrix and vector or a vector by itself. Similarly, g of x times u, depending on the number of inputs you have. This expression has to match in dimensions with the state vector x. Actually, in front of me, I'm seeing only my PPT screen, nothing else. So please do alert me if I'm lost in connection at some point or other.
Yes, sir. Sure, sir.
Okay. Thank you. Okay, so this is the basic framework, right? So what I'm trying to say is that as practical as an induction motor can be modeled in such a mathematical way. Okay. Now, control. These are some of the lines which I just wanted to look at. The rotor speed, rotor fluxes, stator currents. These are the states of the system. Inertia, inductances, mutual inductances, and all these things are the parameters which appear in your um, coefficients. And the voltages, UA and UB, are designed as a function of the whole state, right? So if you do it that way, you'll be able to do some, after linearization, of course, think of a state feedback matrix K so that U equal to Kx may work under some assumptions and conditions. So that was the uh, whole idea as far as control is concerned, and particularly from a machine's perspective, because your preoccupation is using this motor in a particular application. So you may not be really paying so much attention on the control aspect of it. To a large extent, if it works, let it work. So what is it we do is that we tend to make use of a reduced order model by, for example, neglecting the last two states to get a current fed induction motor, right? So in this equation, you can forget about some of these terms which are actually causing linearities, I mean non-linearities. You'll have a reduced order model. You don't even have to have that fifth order or sixth order model. A second order model would do. And then you can have a PI, PID kind of controllers. Now, extending this, and if we'd like to really make use of all the state variables, just now I was mentioning that output is not the only quantity that is available for measurement, but with ingenuity and together with the development in sensor technology, you should be able to measure various other quantities as well. And in fact, I would say that this kind of a problem should pose a challenge to those who are more involved in sensor development, right? Okay, look, in so and so application, there is a need for sensing so and so quantity. Can I develop a sensor for that, right? So we should not be so conservative or meek, saying that this quantity cannot be measured. What can we do about it? Let us forget about it. Let us not get defeated, right? Let us demand what we want. That should be the spirit of research, which obviously takes you much more forward, right? So linear state feedback is something about the understanding of nuances. Nuances means fine details. So not only the output, but perhaps in a canonical way, output, its first derivative, second derivative, and so on. All these are required for us, and each one of them they contribute, right? And we would like to make use of these measurements as state variables, and then a combination, a linear combination of all these state variables will be able to give you a good feedback, and then that feedback is by and large sufficient. That's the whole idea. See, for example, just imagine as a mental exercise, of course, I'm aware that post lunch, these kinds of lectures are deadly. That's why I postponed my lunch. That's a different story. Okay, I'll just give you a small mental exercise. Don't use pens and papers, but try to figure out mentally what you can get. Suppose I have one single state variable, a first order system, and I'll say x of k plus 1 is equal to x of k plus 1. The initial condition is x of 0 equal to 0. So if you iterate on this state equation, the so-called difference equation, if you can quickly identify. So what is it you get for x of 1, x of 2, x of 3, and so on? I hope the question is clear. Starting with x of 0 equal to 0, I'm asking what will be x of 1, 2, 3, and so on if the equation governing the process is x of k plus 1 is equal to x of k plus 1. So that means the next number is the previous number plus 1, correct? Yes or no?
Sir, if k is equal to 0, then the
Yeah.
equation is x of 1 is equal to x of 0 plus 1.
Yeah. So if you start with x of 0 equal to 0, x of 1 becomes 1, correct?
Yes, sir.
So x of 2 is x of 1 plus 1. So it is 1 plus 1, 2.
Mm.
So that's how you'll be able to generate from 0, 1, 2, 3, 4 like that. Right? You are actually able to generate a sequence of all integers starting from 0. Correct?
Yes, sir.
Right. So this is actually a very simple example of what we call as a dynamical system or a differential equation if it is a continuous time one. In fact, if you apply the fundamental principle of calculus and things like that, it is like the differential equation dx by dt equal to 1. X dot equal to 1. If you solve, what is it you get? Dx by dt equal to 1 with the initial condition 0, dx equal to dt, therefore x equal to t plus c, because the initial condition is 0, x of t equal to t. And now if you are discretizing and you are sampling it at certain specific instants, x of 0, x of 1, and so on, you get x of k equal to k. Right. So this is how we look at systems. So I can say that this is an autonomous system taking some initial condition and then it automatically generates all the consecutive integers. Correct? So this is a simple process. Okay, the next question is suppose x of k plus 1 is something like half x of k plus 1. I introduce a coefficient half. So can you please quickly give me the first few numbers you get out of this process, starting from 0? What is x of 1?
It is 1.5, sir.
X of 1 is 1, right?
Ah,
X of 2 is 1.5. X
yes,
of
sir.
3?
2 plus 1.
2.
So that is half of 1.5 plus 1. So it will be
1.7.
1.75. Right. Just find out a few more terms, maybe 2 or 3 more, and tell me if you understand any pattern out of it.
Sir, the pattern is increasing with 0.25. No. No, sir, no.
Okay. No hurry, no hurry. I'm sure you are trying to do it for the first time, but anyway, try to understand that we are actually trying to, at the ground levels, trying to solve the differential equations.
Sir, it goes on like this: x of 0 is equal to 1, x of 1 is equal to 1.5, x of 2 is equal to 1.75, x of 3 is 1.37.
1.875, yes, yeah. Right. So you are slowly approaching 2, correct?
Yes, sir.
But very slowly. For example, the initial jump is very high, 1 to 1.5.
Yes, sir.
Next jump is slightly slower, only
Yes, sir.
0.25. Next is even half of it.
Yes, sir.
Right. So you eventually, maybe slowly, you'll approach 2.
1.
Correct?
1, sir. 1.
1 or 2. You are already at 1.5 and 1.75, right?
Mm.
So you go up to 2,
2.
but you will not go beyond 2.
Yes, sir.
Right. So now, just if you compare, what is it we have got earlier? It was something like 0, 1, 2, 3, 4, 5, 6, something like that. So it is uh, an infinitely growing straight line. It's not bounded, right? If you increase k, let us say k equal to 10, it becomes 10. K equal to 100, it becomes 100. It goes unbounded. Whereas in the second case, what is it we have done? I slightly changed the coefficient. Earlier the coefficient was 1, now I made it half. So with that, I could now kind of bend my curve and then make it bounded by 2. Please recollect some of the basics of stability theory you have studied in controls. Oh, how do you define stability? A bounded input must give bounded output. What is it you mean by bound? The absolute value of a particular signal should not exceed a certain number. If it is exceeding and going towards infinity, it is unbounded. Okay. So the point is now having a process like this, if I tweak the coefficients, I'll be able to control, right? So for example, now as a homework quickly, you can work out what happens if the coefficient is not half, but it is 1/3. What happens if it is 1/4? What happens if it is 2/3? Try it out. You'll understand. In every case, you compare. So first one is unbounded with coefficient 1. With half, it is approaching 2. With 1/4, you will see that it approaches something else. With 2/3, it approaches something else. Some of these are faster than the others and so on. So the story here I want to make it clear that you need to look at it from a different perspective. Is that in any of these dynamical systems, the coefficients are very important. And if you apply Laplace transformation, for example, for the linear case, you get what is called the characteristic polynomial, right? And if you remember, we take the characteristic polynomial as the denominator of your transfer function. And the roots of the characteristic polynomial, we know they are called as poles. And the location of the poles, for example, if they are real and distinct or complex conjugate, something like that, the response will change. Right? That's what we know. But what is it we are unable to see, or what is it we need to really observe here is that if you have a polynomial, in fact, any differential equation will have a polynomial in certain transformation. And polynomials coefficients are related to the roots of the polynomial. So, for example, you have seen if the polynomial begins with coefficient 1, say x power 3, the next one, let us say ax square. A is the negative of sum of all roots. The next one is sum of all products of roots taken two at a time, and so on. So you know there is a relationship among the roots and the coefficients. So if you want to change the poles or so-called roots of the characteristic polynomial, you need to accordingly change the coefficients. And that's exactly where your state feedback u equal to kx will help you, right? So this is the basic model of linear state feedback. That's what I'm talking about as understanding the nuances, right? So what's happening is if you have x dot equal to ax plus bu and u equal to kx, it becomes x dot equal to a plus bkx, right? The eigenvalues or the poles of a are different, a plus bk are different. So if you want to change from one set of poles to another set of poles, that's why the problem is also called as pole placement. You have to find out a particular K matrix such that it will work. So there is the basic idea behind linear state feedback. It is not simply putting to some matrix forms, and then in most of the classical textbooks, older books like Ogata, Nagaratan Gopal and things like that, you find that state feedback is defined. You don't have to define, you can derive it. Okay. So these are all some of the things. Quick example, we'll very quickly go through this. If you take a series RLC circuit, again, you are basically from electrical background, this should be very clear to you. So these are the two equations given a series RLC circuit. Apply Kirchhoff's voltage law and also make use of the elemental law that governs a particular component called the capacitor. So using this, what's it we were doing earlier? I would like to convert the top equation into a second order equation, right? Instead of this first order equation, I would like to make use of this and then convert it into second order equation. And then we talk about underdamped, overdamped, all sorts of things. But instead of that, if you put them in a matrix form like this, you can get one model. For example, here I called the inductor current as x1 and capacitor voltage as x2. Well, very simply, I can call this VC as x1 and IL as x2. I can do that. If you want, I can multiply this IL, that is x1, by some R and then add x2, right? So my state variable, one of them is R times x1 plus x2. Another can be R times x1 minus x2. I can have infinitely many choices of designating these state variables as long as they're physical, right? I'm just trying to establish a connection between the physical quantities right over there and some mathematical concepts. Right. So they can be physical parameters themselves, or you can also have as state variables linear combinations of the physical variables. So each one will give you a different model, right? Barely with this, you get model 1. If I interchange, I get model 2. If I take a linear combination, I get model 3. And I can generate n number of models. And all these models will look like this. This is what we call as state feedback, I mean state space model. And as I said, you can interchange x1, x2, whatever it is. All such fancies, so to say, can be accommodated. You can see the system from different perspectives. Okay. And for example, how do you relate one model with another model, right? So in this, you can see that if in one set, let us say old, here what is it I have taken? X1 is current and X2 is voltage. So let this old vector be current and voltage, new vector be voltage and current. How are these two related? By this matrix, right? Voltage is equal to 0 times current plus voltage. Similarly, current equal to 1 times current plus 0 times voltage. So there is a transformation between older vector and the new vector, correct? So this is what we call as a linear transformation because we don't have squares or any other terms here. And what is it I need to actually observe? It's not just that there is only a matrix here or there are so many zeros and things like that, but the observation we require, that's where some background is required, is that this matrix is so-called orthonormal, meaning that its transpose itself is its inverse. Okay, and more mathematically, and in fact more functionally also, we say that this matrix T is invertible. So any transformation which is invertible is of immense use to us. So that's the moral of the story. And trying to get a relation with a old vector with any new vector using some invertible T matrix is what we call as change of basis. Okay. So these are all some of the mathematical ways of looking at physical systems. This is required because if you are able to abstract, you can do so many things. All right. Maybe you would have learned something about drawing when you joined engineering. Whether you liked it or not, first year, maybe you would have certainly undergone a course in drawing. Then what is it you are taught? Typically, for any object, you are asked to draw what is called the top view. You are supposed to draw what is called the front view. Maybe after a few chapters, you learn to draw what is called the isometric view. So that you see a part of sidewards, a part of front, a part of top, and so on and so forth. Right? Why is this all required? Because when you see it from one angle, things will have a different nature. If you just like that see a house, it is planar. You don't know how many rooms are there behind. You don't know the depth. So you may have to turn around and see it from a different angle to understand that. Right. So these are all various ways of our own typical behavior, but if you add some description to it so that others also understand when you communicate, the language becomes mathematics because there is no ambiguity in this language, right? Compared to English or Tamil or Telugu or any such language, we don't have ambiguity in mathematics. That's why it is chosen. And we'd like to change the basis. That means the frame of reference, whether I'd like to see it from the top or front or side. Just to give you a quick analogy. So this is what we do here. And ultimately, all models are equivalent. That's important. It's only our perspective that is different, but the object there doesn't change. It's the same house. But you are seeing it from this way, somebody else is seeing from another way. That's it. All right. So the design of modern controllers is basically to make use of the characteristic polynomials and the roots and coefficients of these polynomials are quite nicely interlinked. Of course, the relationship is not linear, right? For example, if I double the coefficient, it doesn't double the roots. And it's also not,
లేకుంటే డిలీట్ చేస్తా అంతే కదా
and also it is not possible to solve all the equations to get the roots from coefficients or coefficients from the roots, right? Uh, it's not so easy in general, but still there is a relationship, a one-to-one relationship, and then catching on that, you would like to design controllers. That was what is given to us by these two great people again around World War time. Yeah, that's what I'm saying. Just a piece of paper and maybe a pencil during war time. How brilliantly they worked. We should really appreciate. Right? Though we have not liked history, therefore we chose mathematics and became engineers. Please, sometimes spend some time to look at the history of these developments. Right? For example, IEEE has a lot of material on the history of control systems. Go through that and you'll look at so many wonderful things that have happened in the past. All right. So specifications are a set of n desired poles, right? And then we would like to map them such that I get u, which is the input signal, as a linear combination of all the states kx plus the arbitrary bias or reference r. So ax plus bu becomes a plus bkx plus br. So there is still a forcing function, but the dynamics have changed. The way, say for example, it could have been originally a overdamped system, but now it becomes underdamped system. So there is a change. The roots originally were uh, real and distinct. Now I have made them complex conjugates. So what k that multiplies the matrix B added to A gives eigenvalues that are complex conjugates. Right? That's the basic question. And this is the setup we have. We have a bunch of integrators here which will integrate all the state variables to give the states. And the model is x dot is ax plus bu and u is kx plus some r and y is cx. The output y is cx. Here also we don't really assume that output is only one quantity, but it could be a combination of a selected set of states. Of course, in ideal case, you can think of everything, but the whole point is if you are able to estimate or measure ideally all the state variables, this part we generally don't care because this is just a linear transformation. More in dynamics is of interest to us. Okay. So these are some of the questions which are also to be asked. Again, compared to classical control, in modern control, we'll ask, first of all, can I control? Right? In the classical control, what is it we have done? You are given a plant 1 by s into s plus 1. Then some specifications. Overshoot less than 5%, rise time 3 seconds, settling time 2.5 seconds, whatever it is. Right? And then there is a method available. You quickly use that procedure to design a lead controller, a lag controller, or PID, things like that. But we never asked whether for this given plant we are able to achieve the desired specifications, whether there is a match, right? As somebody put it nicely some time back, if somebody has failed in his elementary school, not even cleared a 10th and things like that, how do you expect any coaching center to coach him to get a seat for him in IIT, right? There is a pertinent question. Of course, coaching centers say that you come study with us, we'll give you a good seat in some good college. But then there are some conditions, right? Suppose I put a 10th failed person who doesn't know anything. whether this coaching helps him, right? Whether the coaching center is successful in giving him a seat. Obviously, no. So we have to ask a question. I'm just trying to dramatize so that with this exaggeration, you see the point more clearly, right? So that's why there are always eligibility criteria. We'll not be able to do every job, though we fancy that, okay, I can, no, if I can drive a car, I can also drive an aeroplane. Yeah, not necessarily. So we need to ask some eligibility questions, which were absent in the classical control. So the question here we ask is it a controllable system? In other words, the question is, does there exist such a state feedback matrix K always? From here onwards, we actually start getting failures. And that's the essence of any development. That's what, if you ask me, I'll strongly say. Only when you see that it is no, then you'll find out what are the limitations. And then, if you are able to distinguish what are the capabilities versus what are the limitations very clearly, you have much more knowledge and understanding about the system. And that's the key. So we go with what's called a rank test. If you remember, B, A, B, A square, B kind of some test by making use of the matrices A and B. And then we'll check whether the composite matrix has full rank or not. If it is full rank, then it is controllable, therefore a K exists. If it is not, it doesn't exist. Okay. So this is how we would have developed. As I said just now, we have B, A, B, A square, B kind of a thing, and then we'll have a test for the ranks. And then if the test fails, there is no controller possible. So that means you'll never be able to achieve the desired specifications. Either you have to change the system or you have to change the specifications. Okay. So this I'll quickly go through because these are some of the things more on the linear part, but I have already covered the essence of it. This is only mathematical part of it. I'll just show you only the results and then I'll take you forward. The point I wanted to drive is, for example, if you take a third order system, right, with the three state variables with A matrix, A square, 3 by 3 matrix, you understand it is a third order system, all right. But if you look at B and it has two columns, you understand that it has two inputs, not one input. So it's not the classical SISO system. Okay. So if a system has two inputs and then, uh, okay, outside I can give you even before testing it. This is a controllable system. And suppose these are my poles to be placed. That means I have to find a K such that A plus BK will have these as eigenvalues. Actually, you can see here that it is more or less like diagonal. If you have studied little more, if you remember, if you recollect, you see that this is what is called the Jordan canonical form. And therefore, there is a 1 here. Otherwise, it would have been a diagonal matrix. Therefore, the eigenvalues are minus 2, and plus 4. Okay. So that means it's an unstable system with a pole on the right half of the S-plane. So I want to make this a stable system and I want all the poles to be like this. Minus 2 I am trying to retain, but the other two poles I want to push them into the left half of the S-plane. This is what I want. So this is my control problem. This is what is given to you. I don't like it because it's unstable. So I want to make it like this. Simple, right? But then this has two inputs. If there are two inputs, what happens is that you can work out and find that a matrix like this will help you, right? A plus bk with the already given A and B matrices will have the eigenvalues or the poles minus 2, minus 3, minus 4. And in general, if the system has multiple inputs, two or more, then it is not a unique solution. You will get many more solutions, right? So this leads to an explosion in the number of possible Ks. That means you have a choice. So that's a good news. There is not just one matrix, but there are multiple matrices K that will solve the problem. That's good. But then there are also difficulties. Suppose if you want to implement using some practical means, let us say in a circuit, you want to implement this using op amps. Op amps, they have some saturation, right? Beyond 12 volts, you can't get anything out of an op amp. So if you impose such constraints, which in turn impose constraints on the K matrix such that the elements of the K matrix are all bounded. Every element of K matrix must be within this interval. And if you want to ask whether such a K matrix exists, of course, your controllability condition says there exists a K matrix. If it is a multiple input system, there exist many more K matrices. But if you specifically ask for a particular K matrix such that its elements are bounded, we really do not know. This is an open problem for a very long time. That's a very interesting research problem. Okay. All right. So far, what is it I have talked about is a bit of linear state space controllers, um, because we are talking about linear systems, and then I was talking something about characteristic polynomials, roots, which are basically what you have called very fondly as poles in your classical control. So control in a little more abstract way is not just getting some overshoot, some rise time, some settling time, and so on, but it is more specifically, more precisely placing the poles at certain locations. And in addition, the systems need not be second order, first order. That means the number of poles, or in general some n, it can be a large number. Then the system need not be restricted to a single input system. There could be multiple number of inputs. That means there are multiple actuators. All right. So this is what I was trying to brief you. Uh, Maybe if there are a couple of questions, we can spend 2 or 3 minutes and then move on to nonlinear part. Any questions, please?
Participants, you can post your queries in chat box. Sir, during last sessions, one of our participants was asking about this bounded matrix and also bounded, and how to decide this, whether it is restricted to using for a system. Based on the system, we need to decide this bounding matrix, like they are posting how to decide this bounding value.
So in this slide, is it? Kij is between Kij underscore and Kij overscore. Is this what you are asking?
Yes, sir. How to
Okay.
decide that values?
Yeah, it is not question of how to decide, but let us look at it simply. Suppose I have a simple circuit, RC circuit. So the voltage across the capacitor can be taken as state variable, and the input U, if it is K times X, right? And for my specification, it may so happen that K times X is exceeding 12 volts. Okay, but how do I get that K? I just have to send this voltage through a voltage amplifier, typically a operational amplifier in its differential mode or whatever it is, and then its output is the amplified version Kx, right? So this K, say X can be anything. Say X can be, for example, 0.12 volts, but I want 12 volts out of it. So that means K must be 100. So the question now is, as an op amp, yes, I can design an op amp that gives a gain of 100, right? I minus R2 by R1 If I choose two resistors, 1:100 ratio, I'll get that.
Mm.
But then if 0.12 is multiplied by 100, I may not get the output as 12 volts because it will have some saturation limits. Right? So that means the gain can be 100, but the actual voltage, if it is not exceeding a certain limit, I will not be able to make use of this op amp. So such restrictions of a particular given system will impose these conditions, right? So that means if the output of the circuit is 0.12, we cannot control better than that. So I have to see that the gain of the amplifier is less than 100. So that K is less than 100. That's how we decide. And in general, it can be on either sides, not necessarily, or you can put it must be between 0 and 100. And in mechanical systems or fluidic systems, you can think of flow saturation. Say, for example, when you open a valve, obviously, when you open a tap, what happens? There is a limit beyond which you cannot get more water, right? You have to obviously wait until some more time, or you may have to break open the pipe. So, saturation limits are quite common in many places. And as I was mentioning, K happens to be the changing factor for the coefficients of the polynomial. So if our K is restricted, possibly the roots are restricted, therefore you will not be able to get the desired response. Or putting the other way, for the given desired response, there could be several Ks, but not exactly the one you are looking for. Say, for example, in this, I have given you something like this, right? So this, what happens if this matrix is multiplying a X, which is a 3 cross 1 vector. So U1 is 6 times X3, right? And U2 is 2 times X1 plus 3 times X2 plus 2 times X3. But this 6 times X3 for U1, the actuator cannot provide that. So I cannot have a 6 here. So this element must be between, let us say, 0 and 5, for example, or it can be from -5 to 5. So such things. So if you actually work out this problem, you may get lots of K matrices. That's what I'm trying to say. But none of those matrices may have the required limit. You may not be able to find a matrix where this is not 6 but 5 or less. Okay. And searching for such one specific matrix out of a lot of matrices that are possible. In fact, there will be infinitely many matrices, even if it is a simple system. Maybe after I share these slides with you, there is an algorithm given here. Try to work out and try to generate your own K matrices. This is only one possible solution. Though it is a simple third order system with the two inputs, you will get infinitely many K matrices. Not two or 2 into 3, 6 and things like that, but infinitely many. Okay. The question is, how long does it take to search for that specific matrix out of a big set of matrices? So that's what I meant by that's it here. But the question, as you are asking, is the limits come out of your actuators. How good is your actuator? How much is its capacity? Right? That's the question. Op amp, for example, has 12 volts as certain limit, saturation limit. Similar things work with valves and other actuators. I hope I'm clear.
Yeah, sir. Yes, sir.
Any other questions or we'll move ahead?
Kindly move ahead, sir.
Okay, thank you. Yeah, so for the next half an hour or so, we will work on the nonlinear part of it. As I said, the framework is now the state space framework where we talk about state variables and how they are interconnected. Right? If it is linear, They are simply multiplied by a matrix. That means you get only linear combinations. So if you read out, x1 dot is a11 x1 plus a12 x2 plus a13 x3. So it's a linear combination of states. For a nonlinear system, this need not be a linear combination. It can be x1 square plus x2 square plus sine x3, something like that. So that's how we have still the same old framework, but some generalizations, some advances, some challenges. Right? Now consider a second order system like this, where x1 dot is not simply 0, 1 into x1, x2, but it is a sine x2. So the nonlinearity comes here, right? Nonlinearity here means if I double x2, sine x2, I mean sine 2x2 is not 2 times sine x2, right? So that's where the nonlinearity plays an important role. Similarly, if you look at the dynamics of the second state variable, x2 dot is minus x1 squared plus u. Similarly, you can just see if I double this x1, I'll get 4 times this. So it is not simply 2x2 dot. Okay. So these are not linear systems. By inspection, by simple testing on the superposition principle, you'll be able to identify these are nonlinear systems. So the question is, how do I control the system? And a more generic question which we are trying to ask is, can we get something like this state feedback as we have done earlier? And why is it you are interested in such a thing? Because it will directly alter the coefficients of the characteristic polynomial, therefore the roots, therefore you'll be able to get the response. So it is such a beautiful framework. If something nice is available, can I have it for nonlinear systems also? Could be a very natural question everybody asks, right? So that's the whole idea. So if you make a transformation like this, earlier I was also talking about some transformations, T matrix, and also it's not just how are the elements looking, what is the dimension of the matrix. That's not the observation that is expected, but what are all the properties that are either evident or that have to be derived from a given matrix. What is it you are trying to look for? I'm trying to look for a matrix that is primarily a invertible matrix. So meaning that the transformation obtained using that invertible matrix is a 1 to 1. From x old using a t, I can go to x new. And with the same t, but its inverse, t inverse, I can get back to x old from x new. So that's what I mean by a 1 to 1 mapping. Okay, so that is important. So we will talk something about a transformation. So let's suppose x1 is called as y1, right? And y2 is a sine x2, which is x1 dot, right, by this equation. So I have a system y1 equal to x1, y2 equal to x1 dot. Okay. Now what happens if you rewrite this? You have now y1 dot equal to y2, right? y1 is x1, so y1 dot is y2. Like your controllable canonical form, x1 dot is equal to x2, x2 dot equal to x3, x2 dot equal to x4, and so on. You write it that way, right? So it is like this. And what is the second equation? What is y2 dot? You have y1 dot, right? First equation is y1 dot. Good. So once you make a transformation from x to y, y1 dot is available. What is y2 dot is the question. So y2 dot is simply differentiate this. What is it I get here? A cos x2 into x2 dot, right? x2 dot is minus x1 square plus u. So this is the transformed version of the system. Okay, originally you are given in terms of x1, x2, you somehow transform, but this transformation is not necessarily a linear transformation like that old T matrix I have shown you. This is a slightly complicated transformation, but yes, it is possible, not only in this example, in many examples, and we also have conditions where such a transformation is not possible also. Okay, so what is it I get here? You simply you can look at some of these things, right? So u times a cos x2 minus x1 square a cos x2 is what you get. So if you get a control signal like this, right, u equal to 1 by a cos x2 v times x1 square. So substitute that 1 by a cos x2 times v plus x1 square. So that will cancel out, and what is it I get is y1 dot equal to y2, all right, and y2 dot is simply v. Okay, so now I have made it as a linear looking system. X1 dot equal to x2, x dot equal to u. So I have a matrix 0 1 0 0 A matrix, and B matrix is 0 1. You can verify that it is controllable, therefore you can have a state feedback. So in the transformed domain, I have my control V as the combination of the two transformed state variables. Now I have a solution. Now what is it I have to do? I have to go back and substitute for what is it? Y and X. So what is it we are trying to give is that this is the system. We convert them, then we propose a linear controller, and then this is made use to generate the nonlinear control law, and then we'll feed the system, right? So from V I get a U, and this U controls the system. So there is an inner loop, this is the original system, and then we have an outer loop, which is a transformed system. So this exactly is what we mean by feedback linearization. So you can actually see that when you choose these transformations, we are coupling. Of course, there is a coupling here also. For example, x1 depends on x2, x2 depends on x1. So there is a coupling or interaction, but in a nonlinear way. And that nonlinear way we are ingeniously conquering by pushing the nonlinearities to the u part and keeping the state variables fairly linear. Right. So in terms of the nonlinearity, we have a linear combination of the transformed ones. Mind you, I was talking about a one-to-one transformation. That means if you are able to get y1 and y2 out of x1 and x2 like this, you should be able to get x1 and x2 out of y1, y2 exactly in a unique way, right? That's the property of the transformation that needs to be maintained. Under those conditions, we are pushing the nonlinearities from the state variables and their interactions to the control signal. And then the control signal will have a negative sign as well. If you carefully understand, that's where we are bringing out here. And that will negate the nonlinearities in the outer loop. So as far as the outer loop is concerned, this is a linearized system for which you have a linear control law. And between linearity and nonlinearity, we have a transformation like this. Okay, so we'll look at some more questions and examples so that we'll understand. So for us, system means a set of differential equations, right? Now for nonlinear systems, we'll have nonlinear differential equations. For example, if you look at a pendulum, it's a nonlinear differential equation with a sine term coming in between. If you look at a robot, it was a nonlinear system. If you look at any aerospace problems, because of the rotations involved and various directions, and you are looking at the forces in various directions, these trigonometric functions will just like that come inside and they create the nonlinearities. So the question is, do we have to live with those nonlinearities or can we change it to our taste? So the transformations are important. So the questions are, do these transformations exist? Okay, at least one transformation. Down the line, we are going to see that under so and so conditions, we can actually get many more transformations. And is the transformation invertible? Right? And how do we get the right one? And then the solution needs n first order differential equations to be solved. By solving, we mean integration, right? As I showed you in the block diagram here. How do you solve the problem? Problem is solved by integrations. So after all these transformations and things like that, these functions are fine so that you can solve by integration. And then finally, in terms of integration, can we completely integrate? Again, going back to your classical control, is it only some set of variables that are integrable or the entire set of state variables integrable? That's the question. So these are some of the questions. And then putting it a little more mathematically, meaning that little more unambiguously, and also accommodating certain possible future questions in the framework. Can we characterize the transformation? Can we give the properties? I don't know the transformation, but I must have certain expectation, right? So for example, this transformation must be an invertible transformation. So that is one way of characterizing. Are there other ways, other properties? Earlier I have shown you T matrix is orthonormal. Orthonormal because orthonormal, what is the advantage? You don't have to explicitly invert the matrix. Just transpose it, you get inverse. Right. So such properties, if the transformation possesses, we call them as characterizations. So can we characterize the transformations? And of course, in the process, can we derive a feedback law? As I just explained, state feedback is essentially changing the coefficients of characteristic polynomial, therefore the roots, and then you are through, right? So this is what we are actually now looking at. So this is how a research problem is made, right? We have learned something which is already there for ages, the so-called linear system theory. And having understood the linear system in finer details, can we use those techniques to solve a nonlinear system? Right? These are some of the things which we need to understand. And this is the way we approach a problem. See, for example, I don't know, most of you might be possessing by now or looking forward to, or at least you are familiar. All of you are familiar with the auto gear cars that are available in the market now, auto transmissions,
Yes, sir.
right? So, have you ever asked? Of course, it's not a big deal at all. I'm just out of curiosity, I'm asking. Maybe when you are children, when you have seen a moped, which is so tempting to drive, even when you're in fifth or sixth standard, if one of our uncles or somebody or maybe our own parents have a moped, which means it doesn't require gears and things like that, just like that cycle. You start, put some petrol, start it, and then you can sit and operating a knob, you can drive. You don't have to pedal. So it's a very tempting thing. But down the line, the complications of changing gears, whether it's a scooter, bike, or a car. So if anyone has asked a question, why not a car without gears? Right? Anyone has asked out of curiosity?
Sir.
Yes, sir. Many times we thought, sir.
Good. So, what were the outcomes of those thoughts? Did you think it was feasible, or did you debate it may not be feasible?
Sir, when we need to go to a slope area,
Yeah.
when then if it does not have a gear system,
Okay.
how do we that is
What?
we
So,
need to
yeah.
have
So you thought that gears will be useful in some
when we
cases.
are
So
when we
yeah.
are climbing a slope and
So you would have thought that maybe it's not a very good idea, but certainly it is convenient if it is possible. Maybe some people would have thought that with such a huge mass, okay, a moped is a light vehicle, but such a huge curb weight, maybe about 1,000 or a little more than that kilograms. Does the machine allow, or how much powerful the machine should be to, simply move it? right? It is something like, I don't know, next week or next 15 days we have Diwali. So we have these rockets and we have a priming for these rockets, right? The rocket actually takes off with its own nozzle and that kind of a mechanism, but to prime it, we put some other chemical
Ignition.
outside. Yeah, ignition.
Yes.
So if you apply those ideas, we understand that whether gear is a necessity because we need to prime it, right?
Yes, sir. Yes, sir.
So these are some of the questions that will come to your mind. Obviously, you keep debating whether it is possible or not possible. Some people say it is possible, so on. Right. So that's exactly what I'm trying to say. If you have learned something, you have seen something, you should be able to look at what else can be done within the same framework. All right. So this is the way I'm trying to develop. Linear systems are very well studied. So much of literature is available. So much of understanding is there from various corners, algebra, geometry, computations, many more, not just engineering systems. All right. If it is so well understood, can we take every bit of it and then try to understand nonlinear systems? Nonlinear systems are difficult. They have nonlinearities. All these things are there, like the geared vehicles. But can I have a huge vehicle, maybe a SUV or even more than that, without gears? Exactly similar way we are formulating the problem. Okay, some more examples like the previous one. If you take x dot equal to axq plus u and y, of course, this was for sake of certain convenience. I typed it this way. Otherwise, it would have been x1 and x2 is x1 and so on. It doesn't matter. Right? There are two state variables here. It's a second order system, but it is a nonlinear system. I'm sorry, this is not y dot. It's y equal to x. Okay, it's a first order system, but it's a nonlinear system because of the cube term. So if you simply take this u equal to minus kx, right, and assuming that the nonlinearity is neglected, that means it's not x cube, but it is as simple as 0. For example, you would have studied so-called nonlinear springs and so on. Or if you expand by Taylor series, that's exactly what we do for Taylor series or linearizing around an operating point and so on and so forth. So forget about this term and then put u equal to minus kx. You think that it can be a stable system. But you can also do it this way, right? You can choose to cancel out this nonlinearity, not just assume that it is getting cancelled, but make sure that it is indeed getting cancelled by way of an opposite sign. Then the system becomes globally asymptotically stable. So these are some of the properties we also need to look forward to when we are designing systems. So one of the important points, as I was saying about characterization of transformation, is that we have to reduce the assumptions. Right? Assumptions we do make in theory, but we evaluate and then we'll also see what happens if a particular assumption is violated. That's important. All right. So another example, this second order here, x1 dot and x2 dot. You have coupled nonlinearities of various things, squares, cubes, products, many things. Right? And then if you make a transformation like z1 is x1 and z2 is a x1 square plus x2, that means pulling out minus 2ax1 from here, right? So if you somehow do this kind of algebra, you will see that u equal to minus k1 z1 minus k2 z2, the outer loop linear system actually has this as the control law, and this system is globally asymptotically stable. Of course, the condition is that if I want this as a part of my input signal, this must be exactly known. So whenever there is a x1, I should be able to quickly square it to get x1 squared and then multiply by the appropriate coefficient a, and then amplified by K2 and then feedback. All right. So these are some of the technical conditions, though out of examples we should be able to observe and then subsequently ask whether they do exist or they do not exist, or what should we do to make them available. Okay, and if you continue with that kind of intuition and then look at this problem, you'll see that it is not linearized by any kind of state feedback control. Right? So that means it is not controllable by feedback linearization. And there could be a lot more counterexamples. So the story is not so rosy. Right? Just as, again, going by your analogy for auto cars and things like that. There are vehicles where you may not be able to do away without gears. Right. So how do we characterize? This is another aspect of characterization of the transformations. Right. So again, expanding, I think I can go up to 3 o'clock. Is it all right, or should I cut short? And
Okay, sir.
okay, it's now 2:40 in my time.
Yes,
Maybe
sir.
by another 15 minutes, I'll try to conclude.
Okay,
Yes,
sir.
sir. Okay, sir.
Okay, the point is now extending our limitations, not just feeling so happy with whatever we have achieved so far, but we would like to go a little farther. But at the same time, we would like to retain a bigger frame. And these are all various dimensions of our thinking. But at the same time, we also want to get as close as possible to reality, right? So the question here is, for example, when you are looking at small things, say for example, around yourself, Earth is flat, right? But if you look at a very large scale, Earth is not flat, right? So that means there is a significant amount of difference between what is local and what is global. So if you are blindly scale up, say for example, I know a small problem, I can do any problem, right? It is a little more than normal foolishness, right? It is something else, which I don't want to use the word. But the point is, we have to be aware that anything will have a limitation, and then how do we accommodate that, and how do we expand our horizons, right? As I was mentioning to somebody else a couple of days ago, if you see something, whether you would like to understand that from your understanding point of view, right? Or would you like to understand from the object's point of view? I hope most of you might have heard a very old story. I don't know if you read it, or at least your grandparents would have read for you. There was an elephant and four blind people. They touch the elephant in different places and then they try to guess what this object is, right? And they come up with very funny answers. None of them they coincide. Each one have their own, perspective, because they are blind. They are unable to see the big elephant. But some of them they would have, say, for example, touched the uh, leg, and then he says, "No, this is a pillar." Somebody would have touched its trunk and then said something else. Somebody would have touched the tail and they would have said something. But all put together is the elephant, right? So that's what is required. So what happens is all of our intuitions, geometries, and things like that, they're fine on lower dimensions, so to say, on a plain paper. And what this slide actually tries to convey to you is that a map you would have used in social studies for map pointing and things like that is a very, very poor replica of the real Earth. To a large extent, maybe the globe is better if you have a globe and study that. And if you open an atlas, you see the pictures are not so linear pictures. In the beginning, you will see something like curved pictures, right, which will try to give you an idea of the curvature of Earth. Right? So, from that perspective, is born a very important subject called differential geometry. Again, this is not a new one. This is at least 200 years old, right? And the ideas or generalizations. What you see, say for example, I draw a triangle, or I draw a rectangle, or I draw another polygon, and then I have a couple of points, and then if I ask uh, what is the geometric picture that connects these 2 points with shortest distance, all of us know it's a straight line, right? But if it is not a piece of paper, plain paper, but if it is a curved surface like the globe, and if you ask the same question, like what is the path between New York and Rome? If you look at the map, they appear to be more or less at the same height. But on the globe, you see that one of them is little further north, right? And if you ask any pilot what is the route, he will not simply go along a straight path, right? He will take a fairly circuitous route, almost like flying up to the North Pole and then coming down towards the Atlantic and then passing through Ireland and then fly across France and then touch Italy, right? So your shortest path, otherwise very intuitively on low scale, is a straight line, all right? But that is no longer straight line if your supporting surface is a curve. Okay, if it is plane, it is straight line, all right. But if it is a curve, it need not be a straight line. That's the moral of the story. So if you make use of this kind of ideas, right? So we can talk something about the straightest curve, which is like a paradox, all right. But we are now making a big picture of all these things, very big picture, right? And very big picture again, the thing is the opposite direction. If you understand this, the linear systems become even more trivial for us, right? Okay, so what is it we do here? I'll not get into every line of this, but I'll tell you something. We have, for example, I started with an example, x of k plus 1 equal to x of k plus 1, and I said that it is actually a differential equation dx by dt equal to 1. So what is happening in all these things is that we are not looking at something that are static with respect to time, but we are like trying to look at functions which change with respect to time. So that's what we actually call as signals. That's why we study a lot of signals, Fourier series and things like that to begin with. An important aspect of all these signals is the rate of change. Right. Another simple observation, which all of you should have done, and in fact, I do it many times, particularly whenever I come to Tirupati railway station. You stand in the middle, the train comes or the train has already come, and then it is there. You have a reservation on the train, say something like S7, right? How do you decide which direction to go? Towards left or towards the right? Do you get my question?
Yes, sir.
Yes, sir.
So you are in the middle, the train is already in front of you. Maybe it shows something like S14, but your reservation is in S7. Which direction do you choose, left or right, and how?
Yes, 14. I'm in science, sir.
So arbitrarily you take up one direction, say left. Then if you see S15, you go
Then
to the
we'll
opposite,
opposite direction.
right?
Yes, sir.
So you're trying to actually differentiate there. You are trying to see how the function is growing, correct? You are trying to look at the progression of the train, whether it is, let's say, the from the engine side, is it in the increasing or decreasing order of the coaches?
Hmm.
And the moment you turn the head this way and that way, and based on that you make a decision, you are actually differentiating. Similar things happen when you drive a car and at some point you want to overtake somebody. What is it you estimate? You would like to estimate how fast that car is moving. Basically, you want to overtake because of the position. Maybe he is very close to you, he is going slow. But then that he is going slow is important, or he is going fast is important before you decide to overtake, right? So differentiation, or the so-called rate of change, and particularly in our cases, rate of change with respect to time, is a very, very important activity. And that's why all of our dynamical systems, the so-called systems, are described by differential equations. Okay. And the differential equations are solved by integration, the opposite of it. Right? How did you verify a subtraction? Subtraction is always a nightmare. Additions are far simpler. But when you're asked to do a subtraction when you're a kid, most of the times we fail, particularly whenever there is a carry, right? But then how did you verify? And how are you feeling happy or confident about your answer? Only by doing the opposite, by adding, right? Your result with the second number, if you add, whether you get the top number or not. So we always do the opposite things. So if you are given a differential equation, you solve it by integration. So the same thing on a larger scale, we do it by what's defining what is called a Lie bracket, right? It is something like the determinant. If you actually look at the way it is written, right? If you have a matrix A, B, C, D in two rows and two columns, how is the determinant given? AD minus BC, right? It is something like this. By the way, a matrix is a generalization of a matrix is a generalization of a um, number, a scalar. All right. So we define something like this, and definitely by now you have been familiar with what are called Jacobians. Right? It is like expanding a given function as a Taylor series and then trying to look at the first term or second term kind of things. Based on that, you decide the size of the Jacobian and so on and so forth. You can do that. And then, of course, this is how, if given two vectors, you can find the bracket, which we write it as this. AD stands for adjoint of G with respect to F. All right. And there are some basic properties in one direction that is opposite in the other direction, right? Much like, again, the determinant. If I interchange the two rows or two columns, what happens to the determinant? It will have an opposite sign. And you can have, for example, a row can be split into two parts. So you get a sum of two matrices. And then what happens to the determinant? You can get it this way, right? And this is an important identity called the Jacobian identity, which again is a cyclic one. So for example, if you see it A, B, C, B, C, A, and CAB, right? It's a cyclic one. And the analogy I can give you here is to quickly remember is something like the Fibonacci series. The third term minus second term minus first term is always 0. Okay, in a Fibonacci series. So this is a very important property. I'm talking about negative signs because of this kind of non-commutative properties. So you can actually reverse the order and have negative signs, and you understand what is it I'm talking about. And the second definition is to look at what are called the partial derivatives of a particular transformation T. And quite interestingly, the transformation you are going to talk about here is not a matrix kind of a transformation which we have seen earlier, but this is more of a scalar function. And we would like to see the rates of change of this scalar function with respect to the coordinates or with respect to the state variables. All right. This is also important because we are talking about multiple dimensions. Right? So we have two state variables, x1 and x2, that describes the x1 and x2 planes. I mean, x1, x2 axis in a plane. Right? So what happens to this transformation along each of these directions is the question. So that's how we call it as the derivative or the differential of the transformation. And then much like your standard inner product or the dot product or also called a scalar product, you have the dot product of a given vector f and the differential of the transformation. Right? So this is something like your complete derivatives. Okay. If you are already familiar with some Jacobian calculations and other things, this is again a generalization of this. As I said, you are free to choose the dimension of the Jacobian. So there are some of these results which can be derived based on the properties and definitions which we have seen earlier. And we have some conditions like controllability, which talk about complete integrability, right? If and only if some conditions are satisfied, and these conditions are in terms of the previously defined dual product, which is like the scalar product, and this must be 0. That means we are talking something about orthogonality. If the dot product of two vectors is 0, you know that they are mutually perpendicular. Right? And for many convenient reasons, we prefer to have mutually perpendicular directions. Right? That's why earlier also I was mentioning about orthonormal. Orthonormal because each of the vectors is a unit vector, 0, 1, 1, 0, if you remember. Right? So it's called orthonormal. Otherwise, it's an orthogonal matrix if each of the columns is perpendicular to the other columns. That's why your identity matrix, for example, it represents your standard XYZ axis. So these are some of the basic generalizations. I just wanted to draw your attention only to these points rather than the fine details, because if you have the big picture first, you can understand these details even faster. And then we have a set of functions. These are all vectors, right? Each one is an n-dimensional vector. F1 is a function of n state variables. F2 is a function of n state variables and so on. And there are m such functions. These are some of the things which you need to pay attention to again. So if you pick up a set of such functions, earlier, again, if you remember, there were ideas of linear combinations or whether they are linearly independent or not, and so on. The same ideas are explained here in terms of functions. There we just took some arbitrary numbers in terms of vectors, and then we asked whether these vectors are linearly independent or linearly dependent. Much the same way we can ask about vectorial functions. Right? For example, f1 can be x1 square, then cos x2 and sin x3. It could be a three-dimensional vector. x1, x2, x3, it is dependent upon. It's a vectorial function. Similarly, I can generate m such functions, and then I ask whether these are independent or not. In linear algebra, they are fairly straightforward results, but in nonlinear algebra, they may not be as straightforward. But still, we do have lots of analogies which will help you understand these things. This is the final theorem. So if you find that these functions are linearly independent and they are completely integrable in the sense that you are able to find transformations and which are mutually orthogonal, then it is involutive. And if it is involutive, that means it is something like your controllability condition where you have, okay, all the things like B, A, B, A square, B having full rank. Right. Only thing is here in terms of functions, G, it's Lie bracket with F, it's Lie bracket with F again, and so on. B, A, B, A squared B, and so on. Look like, I mean, if it is a linearly independent set means the rank of this is n, right? So there exists a T1. If you have a T1, what is it we do is that we simply take T2 as the DT1 and F's dual product, T3 so on. So that's why you get something like the controller canonical form, which we call it as the Brunelleschi form. I showed you here. Where is it? Yeah. Just see x1 dot is x2, x2 dot is x3, and so on. Xn dot or xn minus 1 dot is xn, and then xn dot is u. Right? This is a multiple integrator system. If it is, say, for example, 2 dimensions, it's 0, 1, 0, 0, and this is 0, 1. So it's a double integrator. There's a triple integrator if it is 3, and so on. It's a multiple integrator system. So you are actually transforming a very ugly nonlinear differential equation into a sequence of linear differential equations and pushing the essential nonlinearity part to the end, to the input signal u, and then you negate it with its counter nonlinear function. The rest of the things are linear. So because these are all consecutive differentials, you'll be able to solve it by consecutive integrations. So that's what the whole story is. The algorithm is fairly, that's what I said, we'll meet the old friend, the B, A, B, A square, B rank condition for controllability. So algorithm is first check like what you did for the existence of K matrix there, find whether a T1 exists. If it exists, take it up. Usually it's a very, very simple function, quite surprisingly. And then use T1 to compute T2, use T2 to compute T3 and so on, right? Because if you know x1, x1 dot is x2. So x2 by you get it by differentiating x1 and so on. So that's the whole idea. And then you are pushing all the nonlinearities to the control signal. And that's exactly the last transformation. All right. And very quickly, I'll just take you back to our examples. Right. What is it we have done here? Everywhere, just see, the first part is always linear. Only in the last case, we are bringing the nonlinearity in terms of the control signal. Right? This was 2-dimensional, but in general, for n dimensions, we take it this way. So the algorithm works until the construction of Tn, and Tn gives you the control signal, which is linearizing the feedback system in the outer loop, if you remember the picture I have seen. And if you locally linearize, yes, you see that these conditions are satisfied, therefore it is controllable locally as well, right? This is what we mean by a diffeomorphism or existence of a manifold and things like that. I'm not getting to more technical details. So if you have a simple example like this, x1 dot is a nonlinear function and x2 dot is u, then f of x is this and g of x is this. So you find that there exists a T1 because the rank is full. Therefore, you find a T1 such that this condition is satisfied. And then Based on this, you see whatever is T1, uh, dou T1 by dou X2 must be equal to 0. That means T1 must be chosen such that it is independent of X2, as simple as that. So take T1 equal to X1. Right? A very simple solution. And then if T1 is X1, you can build T2. T1 can be more complicated also, but it is not required. Right? You can begin with simple solutions. So T2 can be computed, and with T2 you can get the transformations, and finally your U as the signal here. Just lastly, one more practical example. You have a motor here rotating some shaft coupled with some spring or maybe a gear kind of a thing arrangement. So the equations are like this. It's a nonlinear system because of this sine term here. And then you can express it in terms of state variables. So you can get Fg. Now it is four-dimensional, a little more complicated, but you find that there exists a T1 and T1 can be as simple as X1. Build T2, T3, T4 from which you can get Y2, Y3, Y4. And then finally your control signal. All right. All right. So this is the whole story. The complications of nonlinear mathematics is a bit too much, so I didn't want to get into things because it's a full semester course. Let me tell you, this cannot be done in 1 or 2 hours time. But I wanted to give you a perspective. Where is the frame? And as I keep mentioning, we need to understand what is available to us completely thoroughly, and then we would like to see in what way it can be extended by asking some interesting questions. And then we should be able to accommodate the new complicated things into our framework. And therefore, we may have to extend our framework a little more, but at the same time ensure that if you remove those extensions, you fall back to your original system. That's what I was also mentioning. Locally, if you linearize, your linear system theory should work there. Okay, so these are some of the approaches of extending ourselves into more complicated, bigger, but definitely practical systems. All right. So that's the message I just wanted to convey. I'm sorry I've taken a little more than the promised time, but still, I hope it is fine as far as it's concerned. And finally, the induction motor I started with is not state feedback linearizable, by the way, though model is there and things like that. You'll find that a T1 doesn't exist in such a case. But these also have messages. It doesn't mean that you have to sit back quietly. If a particular rank condition is not met, it means that you may have to go with an additional actuator. Right? The model is not complete. You may have to make the system a little more complete by adding necessary number of actuators as well as sensors. Depending on the rank condition, mathematically you get it. That's the more serious implication. Right. We have necessary and sufficient conditions, and this is the basic summary. And then there is a lot of creativity. For example, T1 is equal to X1 is a simple solution, but you can prefer to get lots of other functions satisfying these conditions, and you'll be able to generate. And that's exactly where your earlier question, how do you impose constraints? So for example, if something requires tan of x1 and you don't have a mechanism to quickly compute tan of x1, you may have to avoid such solution. So these are some of the things which we require. All right. Thank you so much, and apologies once again for delaying. I think I have taken full 2 hours as per my starting schedule is concerned. I hope at least half of you have liked this talk. Please feel free to write to me whenever you come this side. Please visit NIT Trichy. You know, it's one of the best institutions in the country. We rank number 9 among all the engineering institutions, just next to 8 IITs, first foremost NIT. It's a wonderful place. I'm here for past 25 years. So please do visit this campus, and when you come to visit the campus, you can meet me as well as my other colleague who have already given you one talk yesterday and maybe one more tomorrow, Dr. K. Srinivasan. Right? Thank you so much. If there are any questions, maybe 1 or 2 minutes we can spend.
Sure, sir. Participants, if you have any queries, can ask. Sir, thank you, sir. Thank you very much, sir, for accepting our invitation. Do visit SVEC, sir,
Def-
whenever you come to Tirupati.
Definitely, definitely.
Yes, sir.
I'm
We will
just looking
send.
forward to this COVID to come down because, yes,
We will send
normally in
more
December
students, sir.
first week I used to be there.
Yes, sir.
For the last 3 years I'm not there, but shortly, hopefully COVID comes down and then we'll be there.
Yes. Last year also, our student got All India Gate Rank 1 in EC department, sir.
Oh, wonderful. Where did he join?
Sir, we do not know, sir, where did he
Okay.
join.
Okay.
And most of our students, they will be trying for NIT Trichy, particularly VLSI branch. They are very much interested to join. And
Yes.
few more alumni we have got from instrumentation and control NIT Trichy.
Right, right. Yeah, that's what I'm saying. In our department, as well as a few other places, as we sometimes, get into conversation, we find it quite interesting, and we like it. That okay, this is a good college where we get some good students to work with.
Thank you, sir, for your feedback. We will continue and we will continue the same, sir, for our future, sir.
Sure, sure. All the best to everyone. And once again, please feel free to write to me if you have any doubts or anything. I'll maybe in another 5 minutes I'll share these slides with your coordinator. She should be able to distribute to all of you.
Yes, sir.
Thank you so
Definitely.
much.
Thank you,
Have a
sir.
nice day. Yeah.
Thank
Thank
you,
you,
sir.
sir. Thank you, sir. Good afternoon, sir. Sharvan Kumar, sir.
Good afternoon, ma'am. Good afternoon.
Sorry, sir, for being delayed.
No problem. Even it is good for me also that they have listened the mathematical modeling. They know the procedure now. I will give them the solution now.
Yes,
The
sir.
system I will give now. Okay. Thank you. Good.
Yes, sir.
So should I share my slide?
Yes,
How to
sir.
slide share?
Sir, near
Okay.
to
Present
hand, there
now.
is one
Okay.
symbol, no, sir. Present now.
Okay.
Just you click it, sir.
Yes. Can you see this now?
Yeah, sir.
Yes, sir.
Yeah, sir.
Okay. So should I start?
Sir, once again, sir.
Okay.
Good afternoon, participants. Today, our resource person is Dr. Sharvan Kumar Pahuja. He is working as Associate Professor in Instrumentation and Control Engineering in NIT Jalandhar. Sir has PhD from IIT Delhi, MTech from REC Kurukshetra, BTech from REC Kurukshetra. Sir has several publications in peer-reviewed journals and one The most of them were reputed journals, highly indexed. Sir has several conference publications. Sir has 2 book chapters. Sir has one research project from DSIR. Sir has organized several events. Sir has guiding out 2 students, one of which student has been awarded PhD. Another student has submitted his thesis. Sir has held a different positions from faculty in charge purchase to associate dean of NIT Jalandhar. Sir, we feel proud, sir. We feel honored to have you here, sir. We welcome you,
Thank
sir,
you
for
very
this.
much.
We
Thank you.
welcome.
Thanks for you and inviting me for this particular talk
Thank you, sir.
and giving me the opportunity to talk with the students. They all are students and faculty.
Faculty, sir.
Okay, faculty. This is for all for faculty. Okay.
Yes, sir.
Okay. So thank you. Now I'm going to start this particular the mathematical modeling of the physiological system. You have listened the last talk related to the non-linear control system, various methods used for, and the most important in the this particular physiological control system, the system where the system is. This slide is visible. Next slide is visible or not?
Yes, sir. Visible, sir.
Okay.
Slideshow.
So the most important parameter in the physiological control system is the system. If
Sir,
you know the
kindly click
system,
slideshow, sir.
slideshow. Okay, okay.
Yeah, sir. Yes,
In
sir.
in simple control system term, you have system, the control system, the process, where you can define the system, you can define the relationship between input and output, you can define the feedback system, you can say the response of the system. So the system consisting of the various components. The system consisting of the various components. The same way, in a human body also, it consists of the various organ system. And these organ system, they are independent and they will work for a noble cause. In a control system, we defined the term as a set point. But in a physiological control system, we define the range in the homeostasis. Just like the set point in the control system, the homeostasis